movie, I'll tell you about this plot, which shows the angular momentum of stars versus the halo angular momentum, so log, so average is around 1 or maybe a little below 1. It's a function of stellar mass, and all the red points and all the blue points come from each of these two simulations, where some selected large symbols show the same object in these two simulations. And we see significant variations in some cases, maybe a factor of 2 or even more, between these two simulations. Yeah?
How long did it take for the blue and red point to be obviously different?
Yeah, so it takes, we'll get to plots as a function of time, but typically it takes gigayears.
But I mean, like, at the very beginning, for them to, like, a few, right when you were starting, like,
yeah.
How long?
Yeah, so you can already see them separated very quickly, but
okay.
by just a little bit, yeah. But for the overall system to change, it takes a few gigayears. And what's really nice here is that you can actually see that the galaxies largely are rotated in opposite ways. So it's like almost 180 degrees between the angular momentum of these two galaxies at the final time. Okay, so we digress a little bit from angular momentum and then come back to it at the end. So I just want to tell you a little bit more about this set of simulations. So indeed, these deviations, as you can see, the overall appearance of the galaxy sometimes is significantly different, and indeed, not only angular momentum changes between them, but also some other quantities. So what's shown here is the difference between pairs of what we call shadow simulations, which form from essentially the same initial conditions, slight perturbations. By the way, I should say you can induce these perturbations just by stopping the simulation and then restarting it on a different number of cores, of compute cores, because then you get different round of errors which are essentially identical to just changing by hand some bits. And what we see is the distribution between such of the maximum velocity, maximum circular velocity of these pairs of shadow galaxies. In this case, we also explored this as a function of resolution. We see that it's essentially resolution independent. We can show this, so then I take this distribution, it's just the width of this distribution is kind of the typical random component of this quantity. And then I show on the y-axis here the width of these distributions as a function of time for different quantities. So we see, for example, the maximum circular velocity, the same quantity as here. It starts very low and it evolves over time to kind of a percent level. So this is true for stellar mass. For stellar mass at low resolution, you can actually see that this comes from Poisson models. Just the number of particles is not very large. But as you increase the number of particles, the result converges way, way faster than what you would expect just from these dashed lines that show the samples. So this is true for many galaxy quantities, and then you can also combine quantities into scaling relations. So this is the Thaler-Fisher scaling relation, if you want, the maximum circular velocity as a function of stellar mass. And again, all these little points show just the overall galaxy population with 3 colors, 3 shadow simulations. And again, these individual symbols show you that the same galaxy scatters around the relation to a degree that may be comparable to the actual overall scatter in the relation. And this is what these plots show, again, as a function of time for different, now not single quantities, but scaling relations, the fraction of the overall scatter in the relation that can be associated to these differences between shadow simulations. So in some sense, this tells you how predictable, how much information you can get from this scatter. What deterministic properties this scatter is actually related to. And I want to just mention a paper that I found really cool that came out just a few weeks ago on the archive. But they did some very simple setup, just a 3-body problem, which they scale in a certain way to say that these are a triple of supermassive black holes merging. And then they have this code that can do n-body dynamics with arbitrary precision. So they set the code to work a precision of 10 to the minus 51, which is the ratio between a parsec where they set up the simulation, and the Planck scale. And I've actually shown that even with this precision, there's a reasonable fraction of their systems that evolve in different ways, that diverge, essentially they are chaotic in this case. So I think, I don't want to make really just very strong statements, but I think it's interesting to think about things in the real universe that can see these kind of perturbations that are implied by hand. Okay, going back to angular momentum. So in this plot, we show the angular momentum modulus of two galaxy populations from two shadow simulations like this. So what's the angular momentum in one simulation versus the other? You see the overall spread is about a factor of 2 in the angular momentum modulus, and then you can do the same kind of plot that we've shown already, and actually you find that maybe for the modulus, actually the result doesn't converge to within the range of resolution that I was able to run. So, but at least at this red curve is actually pretty high resolution for those of you. It's meaningful. It's close to the TNG50 resolution, and you see that still at this level, it's about 10 or 20% of their overall scatter in the angular momentum versus mass relation. What about the angle? And this will be the last thing I'll talk about. We also see some difference in the angle between the angular momentum between these two shadows. It's about 15 degrees in the median. And the question is then, what should we compare this 15 degrees to? So I'm comparing this to the degree of reorientation of the angular momentum over cosmic time. And maybe I'll skip this. So if we plot we can plot the histogram of the reorientation angle, something we already looked at in blue here, and then the histogram of the difference in reorientation angles between two shadows. So this is what we get, and the question is, so what's actually the size of the chaotic component of this? So apparently this can be pretty well fit by a simple model where each galaxy has two components to the reorientation that it undergoes over cosmic time. One is a deterministic component, and then around that it also has some local, some additional random variation. So these distributions for high angular momentum galaxies, for these galaxies, can be explained by a simple model like that, where again we just prescribe the degree of deterministic and random component, and we plot. So if you can see these dashed lines underlying the thick lines are from a model like this. So what it shows is, it's just 4 different galaxies. Each of them has a deterministic reorientation angle, and then around it a bunch of random components, and you can essentially reproduce this very well for these galaxies with a deterministic reorientation of 40 degrees and random reorientation of 14 degrees. Now if we look at low J galaxies, this looks more like this. We have a deterministic reorientation of something around 20 degrees typically, and the random component of about 80 degrees, and we can reproduce these observations well. Okay, and this comes back to the puzzle that I left from a few slides ago. How come we have significant reorientation over cosmic time, but in the end, the misalignment between dark matter and stars looks in the final state very similar to the initial state, and this comes from the fact that the reorientation here is random, and here is more deterministic, and you can, with this model, it's easy to reproduce this small difference even after significant random reorientation angles. Okay, so I'll stop here. Some simple takeaway messages. Stars don't form from a fair sample of dark matter in the initial conditions in terms of their angular momentum. It's a biased sample in the Lagrangian patch. These galaxies form in more self-aligned environment. Their halos, the dark matter in the halos, as well as in their large-scale environment at the turnaround time is more self-coherent. Strong angular momentum changes over cosmic time lead to an almost complete decoupling between the modulus of angular momentum of stars and the dark matter halos, but the direction, in particular for these galaxies, remains fairly constant over time, with perhaps implications for intrinsic alignments. And finally, there is a significant chaotic component to the angular momentum of galaxies. Thank you for listening.
had some questions during the talk. I think we've probably got some time for a few more.
About the cozy component, so is it coming in your simulations? Is it coming mostly from the equations itself, or is it like from the numerical method?
Yeah, very good question. I don't have you know, super robust answer to this, but I think something like the arbitrary precision exercise that I've shown suggests that there's. I mean, we know that the three-body problem is chaotic, right? So, so we know that there is actually physical chaos. To what degree this can be separated from the numerics, I think it's hard. I think I don't know the answer fully. I've asked this question many people as I was just starting to work on this project. Everyone just told me perform resolution convergence tests. That's the best answer anyone could give me. So I've done that, and yeah, some things converge and some things don't. So I think definitely there's more work that can be done.
I think this scatter the simulations with like 10 to the minus 50. Is it similar to that in your simulations, or I mean for points you can compare?
We can't make a direct comparison. It was very simple.
Okay.
Very simple setup. So in terms of the initial perturbations, that is.
No, final. Let's say. Probes that can be compared to.
I don't know. I mean, they really have this three-body problem. It's like I can't compare it to a cosmological simulation.
I think there is a difference between chaotic and between instabilities. Here in